Hello, everyone. My name is Efi, and let me start by saying thank you for joining this session. It's not trivial, especially when there are so many good sessions around us, and I really hope to make it worth it. It's my first time on stage at re:Invent, so I'm a bit nervous, and I hope you'll understand that. A couple words about technical prerequisites for this session. I expect you to know and to use AWS Lambda. I'm going to talk also about Rust, of course, but I don't expect you to know how to code in Rust. I'm going to highlight the important points when showing code in Rust. In addition, I'm going to share with you at the end of the session a link to a GitHub repository containing all the source code. So even if you don't fully understand everything right now, you'll be able to go over the code on your own free time and better understand it. So let's start. So I want to start with a story. And I'm quite sure that many of you, either in the past or even right now, have a very similar story. Meet Gamma Ray. Gamma Ray is a fictional company that develops AWS tools for AWS developers. A couple of years ago, due to customer demand, we've decided to extend our line of products and add a new product that enables you to manage your S3 buckets. We are a very MVP-oriented company. So, of course, we chose serverless, and we used Python in order to develop our code. And we got really rave reviews on the first release. Our early adopters really liked what we did. And as time moved on, more and more customers joined the product. And of course, we started adding more and more features and capabilities. Then we started getting complaints. Well, people are always complaining. They're never satisfied with what they have, unfortunately. And we started getting complaints from, on one side, from our customers, complaining on sluggish interface. And on the other side, from our company CFO, complaining about skyrocketing IT budget. I was the head of R&D, and it was my and the R&D time to shine again. So we worked really hard on refactoring the application, changing code, and we managed to tackle the major pillars of performance and cost. But as time moved on, we understood that what hinders us the most is the runtime that we chose, specifically Python, and the packages that we used, Boto 3. So we've decided to search for another runtime. So we've looked and searched and reviewed, and eventually we chose Rust. Why Rust? For two main reasons: performance and great and amazing support for concurrency. The purpose of this session is to share with you the journey that we did in transforming our existing Python serverless application to use Rust. So, as the head of R&D and as a developer in my own free time, the ability to rewrite everything in Rust was exactly what I wanted. But let's be honest, it's not practical. We have a working application, something that brings a lot of money every month. The last thing that we really wanted to do was to rewrite everything in Rust. So I want to share with you three strategies during this session, three strategies that we used in order to add some Rust magic into an existing app, into an existing Python application. I'm going to start with Rust bindings, in which we're adding Rust to an existing Python Lambda. Next, I'm going to talk about choosing a very specific Lambda and rewriting it from scratch using AWSM and Rust. And last but not least, I'm going to show you how to share common behaviors across a fleet of Lambdas using Lambda extensions. All of these solutions, all of these strategies varies in their performance improvement, how much work is needed in order to implement them, and whether they affect a single line of code, a single Lambda, or a fleet of Lambdas. And I'm going to talk about these issues when talking about the different strategies. So for those who are not familiar with Rust, a one-liner. What is Rust? Rust is a programming language, focuses on safety, performance, and concurrency. And of course, you are more than welcome to read online. As I mentioned earlier, I'm going to have the source code at the end of the session. The source code is available on GitHub. So in addition to the different strategies that I'm going to share with you, The source code also contains a dev container configuration with all the relevant tools and their respective configuration that I'm going to show you during this presentation, which you need in order to develop Rust for serverless. So it's not only code. A couple words about me. My name is Efi. I'm a senior cloud architect at Cloudex. I'm an AWS serverless hero, and I'm the maintainer of a GitHub organization aims at improving existing AWS CLI tools by adding some Rust magic into them. So the agenda. I'm going to go do a quick overview of the architecture that we are rebuilding with Rust. And next, I'm going to deep dive into each of the strategies. I'm going to talk about Rust bindings, about writing a Rust Lambda from scratch, and then end using Lambda extensions. So let's start with the architecture, the high-level architecture of the application. This is a really classic serverless application. Okay, it contains an API gateway that authenticates and authorizes all the requests through an authorizer Lambda. The authorizer Lambda pulls the relevant data from the headers, checks them against the DynamoDB. If the request is approved, then the relevant Lambda is being called. In our case, I'm going to concentrate on a very specific Lambda called list buckets, which, as its name suggests, it lists all the available buckets in the customer's account. And as the application grew, more and more teams joined the effort. And although most of the application is written using Python, some Lambdas were also written using Node and Java. Why? I don't know. We are deploying the application to production using AWSM. So let's start with the first strategy. So I'm going to zoom in into the list buckets flow. So this is a very interesting Lambda. This is a front-facing Lambda. And it's actually being used in many of our customers' dashboards. And we knew that by improving its performance and reducing its cost, it will affect our entire application. The biggest problem with this Lambda is that it's a complex Lambda. And we were really afraid to write everything from scratch using Rust. So instead, we chose a different strategy. We've decided to use Rust bindings. So in Rust bindings, we're looking for code that could be replaced by Rust. We did some profiling and found out that this piece of code is the slowest part in the Lambda. And if you look at it, it's a very simple code. It lists all the available buckets in the customer's account using both of three. And next, using async, it goes over all the buckets and finds their respective regions. Again, it's very simple code. So we've decided to replace this code with Rust. For that, we were using two tools. The first tool is called Pio3. Pio3 is a crate. So for those who are not familiar with Rust, a crate is just like a package in Python. You can add external dependencies to your code. And what this crate is doing, it exposes Rust code as standard Python interface. For example, you can add a Python module, a Python class, a Python method, and behind the scene, everything is written using Rust. Rust is a native language, which means that in the end, you compile it to a binary that runs in the machine. So you need a tool to compile it, build it, link it, and this is what Maturin is used for. Maturin is a command line interface tool that does all the things that I've mentioned. But in addition to building the binary, it also knows how to package the binary into a standard Python package, a wheel package, WHL. So you can use this package in your regular Python application. So let's see how we can use Pio3 in order to write our code. So this is an example of the code. Again, I'm not going to show you the entire code in Rust. Again, you can go later on to the repository and read the code on your own. So here I'm using an attribute, a Pio3 attribute called PyModule to define a new Python module. You can see that I'm adding a new class to the module. The name of the class is S3OpsRust. Next, I want to define the class, how the class looks like. So again, I'm using an attribute called PyClass to define a Python class. I'm putting it on a struct, on a Rust struct. And next, I'm defining the various methods that I want to define for the class. So I'm defining two methods here. The first one is a constructor. The constructor is important. Why? We are using Lambda, and I want to instantiate all of our client, of the SDK client, outside of the handler in order to improve warm start performance. So I'm creating a constructor, and in the constructor, I'm going to instantiate the Rust SDK client. And next, I'm defining the rest of the methods, which is list buckets in our case. But of course, you can add how many methods that you want. So before diving into how to compile and build the code, I want to first go over the SDK, the Rust SDK. So thankfully, AWS released a Rust SDK, and it's amazing. And the only caveat when using the SDK is that it's in developer preview mode. What does it mean in developer preview mode? It means that they do not recommend to use it in production. So I'll be honest with you. I've been using this SDK for the last couple of months, and it works flawlessly. The only thing that does change is the interface. But I think that with proper wrapping or abstraction, you can mitigate the issue. So if there's anyone here from the Rust SDK team, I think you did really fabulous work, and you can just put it out of beta, on developer preview mode. Next, you can define the client itself. So just like if you've used an AWS SDK in the past, it's very similar. You define a client. You define the relevant configuration to this client, like the region and secrets. And that's it, as simple as that. And each client has the relevant methods to use in order to call the service that you need. As simple as 1, 2, 3. What I really like about the Rust SDK, that unlike certain other runtime, Python, it has built support for async. So it's really the SDK, again, because the Rust runtime supports async out of the box, the Rust SDK also supports async out of the box, and it's really, really fast. And I highly recommend that when you use the Rust SDK, to use its async capabilities. It's so fast that many times it happened to me that I've reached the service limitations. Even with lower memory configuration for the Lambda, I very easily, for example, the number of calls I can do against an S3 bucket, very easily I'm reaching that limitation. So I recommend baking into your code either a retry or a rate limiting mechanism. I think that the SDK contains a retry as part of the SDK. And for rate limiting, you can use a crate. No need to reinvent the wheel for that. So we wrote the code, and we used the SDK, and we are ready to package everything. Remember, we have Rust code. We need to build it, compile it, link it, create a binary, and somehow use it in our Python application. And this is what Maturin is used for. A couple of notes when using Maturin. I highly recommend using it when releasing your binary to release it in release mode, in production mode, mainly because Rust Python in debug mode is very big in size, a couple of hundreds of megabytes in size. And if you are using the zip packaging system for your Lambda, you won't be able to deploy your Lambda because it's too big. In case you do want to use debug mode for your Rust code for any reason, then you'll need to use a Docker, a container deployment system for your Lambda. So next, because Rust is a binary, a native binary, you have to compile it against libraries that are found in the Lambda runtime. So you have to make sure that, if you compile your code in your MacBook, when you try to run it in your Lambda, you get libc errors or libraries not found. So you can use either the Zig flag or the compatibility flag in order to make sure that your final binary can be used in your Lambda. So in the end, Maturin produces a package which you can use in your favorite package manager in Python, either it's pip or whatever you want to use, and it just works out of the box, very simple. And how do you use the code? That's what's really nice about PyO3. We've created a module, we've created a class, we've created a relevant method, so you can just import the module, instantiate your class outside of the handler, again, for improved warm start performance, and use the relevant methods that you need. Very simple, very straightforward. One caveat when using AWSM. AWSM caches your artifacts when you're building your Lambda. So whenever you're doing changes in your Rust code and you are recompiling it, AWSM won't catch the changes. So don't ask me how I know. I've wasted too many hours in trying to find out why my code changes that I did are not running in the cloud. So if you are building your Rust library for your Lambda, make sure to either disable the cache or delete the cache folder for AWSM. Another thing to remember is that because your package doesn't contain the source code, you won't have any code hints in your editor. And I'm sure you want code hints. Sure, you want autocomplete, and so on. So you can use Python interface stub files. You can put the stub file in your root folder of your Rust library, and Maturin will automatically pick the interface file and will package it as part of your final package. And how does the interface file look like? It's a very simple stub that doesn't contain any code. It just contains the definitions, names, code hints, and description. Great. So we are talking about performance. So show me the performance. You're just talking only on code. Show me how did it really improve the performance and cost. So we've used two tools in order to measure our performance and cost. The first tool developed by Jan Kooi and Lumigo that measures cold start performance. And the second tool developed by Alex Casalboni, and I hope I'm pronouncing his name correctly, which develops the Lambda Pi tuning tool, which helps us to measure warm start and cost. So let's look at the numbers. Really great numbers, if you ask me. So one thing so first of all, the x-axis here contains the amount of memory for the Lambda. Remember, more memory means more CPU power, but it also means that you pay more money. And the y-axis contains the average latency of your Lambda. The blue line is Python, and the green line is Rust. Two interesting points. First of all, you can see that both Python and Rust are comparable in performance for the piece of code that I showed you earlier when using 1 GB of memory. But, and here comes the magic, when using Rust, you get the same performance even with lower memory configuration. And this is a recurring theme for Rust. You can use less memory, therefore pay less money, and you get either better or same performance. And again, if we look at the amount of how much money we've paid for the invocation, so it's very similar to the previous graph. Here, the y-axis is the cost per 1 million invocations. And again, you can see that Rust, on average, is 3 to 4 times cheaper compared to Python. And if we zoom in into a very specific memory configuration, you can see that Python is 3 times slower and 3 times more expensive when using 256 megabytes. Amazing. I want to show you the cold start performance. But before actually seeing the numbers, I want to first discuss whether we should care about cold start and why cold start were important to us. So most of the time, you shouldn't really care about cold start. 2 main reasons. First of all, AWS is still doing very great job in improving the cold start performance without you paying any dollars for that. Yeah, it's snap start, improved SDKs, ahead of time invocations. It does really a lot of good work behind the scenes, so you won't care. By the way, I specifically omitted provision concurrency because it costs money, and we really wanted to reduce the cold start performance without paying extra money. But again, it's a valid solution. It's really okay to use it. So another reason why cold start, you shouldn't really care about cold start is if you're using your Lambda in a batch processing behind the scenes, this extra 100, 200 milliseconds, you shouldn't really care about them. But in our case, our Lambda were front-facing Lambdas. It means that these extra 100, 200 milliseconds hindered our customer experience. They didn't get what we wanted them to get. So it was very important for us to improve the cold start performance. So let's look at the numbers. Again, the numbers are fantastic. Look at it, 3 times faster. And when you really think about it, listen, the Python code is around 50 lines of code. Rust is more verbose, 50 lines, 60 lines of code. But without too much effort, we managed to improve cost, performance of warm start and cold start. And we were really puzzled to understand, of course, it's Rust, it's very fast, but what made this different? I mean, we didn't really replace the entire Lambda. We just replaced a couple of lines of code. And we had an hypothesis. And the name of the hypothesis is Boto3. So I'll be honest with you. I really love Boto3, and I think it's a wonderful package, but it's bloated. Okay? It takes a lot of precious disk space, and your zip file is very big. And I don't know. I've never looked at the code, but I'm sure that things are not optimized. It's Python in the end. So just by replacing Boto3 with the Rust SDK, in the end, that's what we did. We used Rust bindings in order to replace the Boto3. We managed to get this performance. And it's amazing. OK, so we've talked about the first strategy. So let's do a quick recap. We had one Lambda that lists all the buckets in our customer's account. It's a complex Lambda. We were afraid to rewrite it from scratch. Therefore, we used Rust bindings in order to replace several lines of code that we thought are slow. And we used Rust in order to replace the code, and we managed to gain quite a lot of performance and cost improvement. And it didn't require a lot of work from our side. Now I want to talk about the second strategy, about rewriting a Lambda from scratch using Rust. This is our authorization and authentication Lambda. Think about it. This is a major hub in the application. Every request that goes through to our application goes through this Lambda. If we could only improve the cost performance of this Lambda, it will improve it across the entire application. And best of all, it's a simple Lambda. Think about it. It's a Lambda that does one thing. I've highlighted the most important line in this Lambda. It pulls the token from the authorization header and it checks it against a DynamoDB table. That's the only thing that it does. And if the value exists, it approves the request. And if not, it drops the request. And that's it. That's the code. It's really simple. And it's a perfect candidate for a complete Rust rewrite. We knew that we are not taking a big risk here. So in order to rewrite completely in Rust, we are using 2 tools. Remember, when using Rust, you need always 2 tools. It might be the same tool, but you always need 2 functions. One, to build, compile, and link to make a binary, and second, to deploy it. So we are using here AWS SAM in order to deploy a Lambda. AWS SAM supports Rust Lambdas out of the box. And we are using Cargo Lambda in order to build and link our binary application. You don't need to know how to use Cargo Lambda. AWS SAM is using it behind the scene. So before writing our Lambda and reviewing the code, I want to make sure that we all understand what happens behind the scene when invoking our Lambda, because it's important to understand it in order to write your Rust code. So we have our Lambda service. It's the service. We can't touch it, something that is developed by AWS, and it is the service that drives the entire flow. Whenever you have a Lambda invocation, your execution environment starts. It's a container that contains your runtime definition. It contains the memory allocation, the timeout. Next, you have the runtime API. The runtime API, again, it's not something under our control as developers. It's something that AWS develops. It's the thing that bridges between the Lambda service and whatever happens inside the execution environment. Next, we have two modules that are under our control. The first is your code, the handler that you use. You write the code that you write. And next, you need a module that knows how to bridge between the runtime API and your code. And this is the runtime. The runtime is doing something very simple. It understands the language of the runtime API and translates it to your code. And on the other way around, it understands what your code is doing and translates it to the runtime API. For example, you have an invocation. The runtime knows how to translate the invocation details to an event that your Python code understands, a dictionary, a real Python dictionary. And on the other side, you have a Python exception. The runtime knows how to translate the Python exception into something that the runtime API understands, an error. So this is an example of how a runtime might look like. It's a Python runtime. I've copied from the Python runtime in GitHub. And of course, I omitted most of the code. And you can see that it looks like an event loop. It's an infinite loop that's waiting for events from the runtime API, translates them, and invokes a Lambda handler, and vice versa. Not all runtimes are created equal, unfortunately. There are runtimes that you can choose in your console, in the AWS console, or in your favorite infrastructure as code tool, Python, Node, Java, and so on. And the question that you should ask is, OK, what happens to runtimes that you can choose? Rust, for example. Well, we saw earlier that a runtime is a required component. Without a runtime, you can't write your Lambda. You can't write your handler. It means that you have to implement your own runtime for Rust. Sounds like a lot of work. It is, but thankfully, you don't have to write it. So again, the AWS team did a really wonderful work in writing a runtime for Rust as a crate. Again, you can use the crate in your own code. The runtime itself, the repository, contains more crates that we are going to talk about them later on during the session. But what you should always remember when writing Rust code is that you have to develop a Lambda in Rust, is that you have to develop two things. You have to develop your handler, and you have to write the runtime. And I'm going to show you here in the code, and usually I'm going to write everything in the same binary. You are not going to create two binaries. And I'm going to show you here right now how to write both the runtime and your handler in the same piece of code. So let's start by writing the runtime. I know it might look complex, especially for those who are not familiar with Rust, but I promise you, it's a template. All you have to do, it keeps repeating itself. The way the runtime looks like, it looks the same over and over again. So you can really copy it. Every time you need to write a Lambda in Rust, you can copy this template over and over again. So we are defining here an async method in Rust. We are defining clients that we use in our code outside of the handler, again, in order to improve warm start performance. Next, we are wrapping a closure using a closure, our handler, our Rust handler. And next, we are taking this closure and using the Lambda runtime event loop, very similar to the event loop we saw in Python. So this is the Rust runtime implementation, and run our closure. And the magic happens behind the scene, and you shouldn't really care what happens behind the scene. So we wrote here the runtime. In the same piece of code, in the same file, you can write also the handler. So again, I'm not going over the entire handler code. Just showing you a snippet. So for those who are not familiar, Rust is a statically typed language. It means that you have to define variable and for each argument, you have to define its type. Thankfully, again, the AWS team provided us a crate for all the available types for your Lambda handler. The name of the crate is AWS Lambda Events. Pay attention that when you are using this crate, add only the events that you need for your handler. So if you're using API Gateway, add only the events that are related to API Gateway, and so on. Otherwise, just increase the size of your final binary without any need for it. So we wrote the code. Let's see how we can use it in AWS SAM. So as I said earlier, AWS SAM supports Rust out of the box. And you define a build method using Cargo Lambda. Again, Cargo Lambda is the tool behind the scene that AWS SAM is using to build and package your binary. And you really shouldn't care what it does. It just calls it. Next, it defines the handler. Again, because we are using Cargo Lambda, the name of the handler is a constant value of, it's called Bootstrap. That's its name. You can't change it. And next, you define the runtime. Again, because we are building our own runtime, so the runtime that we define here is called provided. Pay attention when using provided with Amazon Linux 2. A month ago, the AWS Lambda team also released support for Amazon 2023. So I didn't check it. I didn't test it with the new runtime, the new provided runtime. But I think it should work. But remember that you have these two options. You can use either Amazon Linux 2 or Amazon 2023. One caveat regarding AWS SAM. Right now, Rust is considered a beta feature in AWS SAM. And again, I really don't know why. It really works good. So again, if there's anyone here from the AWS team, you did a really good job, and you can put it out of beta. So you have to remember to enable the relevant flag or change the relevant configuration to support beta in AWS SAM. Performance, again, very important. That's why we are here. Again, I'm using the two tools to measure cold start and warm start performance. So again, the numbers are fantastic. You can see that for Rust, there isn't really any need to use anything that is more than 128 megabytes of memory. It's, I don't know, it's around 4 times faster than Python. And of course, paying much less money. And regarding cost, pay attention that the y-axis here is per 100 million invocations. And again, the numbers are great. Rust is, again, it's 3 times to 4 times cheaper compared to Python. And if we zoom in into a very specific number, 128 megabytes, you can see that, again, Python is 4 times slower and 4 times more expensive. Now comes the kicker, the cold start performance. This is the main reason why we wrote everything in Rust. Look at these numbers. It's 6 times, 7 times faster compared to Python. And this is a major win. I mean, this is why we moved to Rust, to see this kind of performance. And really, rewriting everything in Rust has its downsides, because it's more complicated, let's be honest, but the performance gains are really amazing. So again, let's do a quick recap before moving to the third strategy. We had a Lambda, which was a major hub in the application. All requests went through it. We prefer to rewrite everything in Rust because the Lambda wasn't too complicated, too complex, in order to gain the full benefits of using Rust. So in addition to writing the handler code, to rewrite the handler code, we also had to add a Rust runtime. But again, thanks to the existing crate and existing code, we didn't have to reinvent the wheel, and it wasn't that complicated to write the new Rust Lambda. So let's talk about the third strategy. So as time moved on, more and more features were added, and more teams joined the effort. And again, these teams decided to use something different. They decided to write code in Java and in Node.js. But one recurring theme or one recurring flow across the entire application, across all these Lambdas, was the analytics flow. All of the Lambdas collected some kind of analytics information and sent the analytics information to an SQS queue. And later on, the messages in the SQS queue were digested by another Lambda. So originally, we wrote the analytics code for each runtime. So we had send to SQS in Java, send to SQS in Node, and in Python. Originally, it was very easy. I mean, that's what the code did, only called the relevant SDK API method. But as time moved on, we wanted to add more features and more capabilities that will improve the performance of the Lambdas and make them more resilient. For example, retry or batching. And we really didn't want to write this code. In the end, it's a dangerous code. And we didn't want to write this code over and over again each time in a different runtime. So we've decided to use Lambda extensions. So I want to explain, before moving on and explaining why Lambda extension and why Rust for writing Lambda extensions, I want to extend the mental model of the execution environment that you saw earlier and understand how Lambda extensions fit into the picture. So we have the Lambda service. We have the runtime API that talks with the runtime, which talks with your code, and so on and so on. The extension itself is a different process. It's a process that runs alongside your handler. It shares the same CPU and memory. It has its own lifecycle events and its own API. And usually your code, again, if you choose to, if it wants to interact with the extension, you are using inter-process communication. For example, an HTTP server. So we have our extension. So the real question is, why use an extension in the analytics case that I've just described? What are the benefits of using an extension here? So two main benefits. First, extensions gives you concurrency support for, again, runtimes that has less than ideal concurrency support. Again, Python as an example. You can start a long-running job in the background, pass it to your extension, your Lambda does what it needs to do, and in the end, before finishing the execution, you pull the value, the content of the result from the extension, and again, do whatever you want to do with it. That's one thing. But what I really like about the extension is it has a very unique life cycle. Usually, when writing your Lambda, and you are returning back a response, your execution environment will freeze. Nothing keeps running. That's it. You finished running. But with an extension, magic happens. You can actually return back a response, but your execution environment keeps running. The code in your extension keeps running. And what's really nice about it is, when you think about it, it really fits the analytics flow that I've just described. The Lambda is doing something. Our user doesn't really care about the analytics, but we have to send it. We have to gather the information. We have to send it in the end to the SQS queue. So instead of letting the user wait another 100 to 200 milliseconds so we'll be able to send our data to the SQS, we can return response immediately. And in the background, our extension keeps running and sends the data to the SQS. Really magic, if you think about it. And of course, it doesn't come for free. You are paying money for it, but you're only paying money for it. You're not paying in latency for it. So the next question is, great, we are using extension. Why Rust? Two main reasons. Extensions are a separate process that shares the same resources as your handler. You probably want something that is efficient and small and runs fast. And that's exactly what Rust is doing. And another reason is that because Rust is native, it doesn't require any runtime with it. Unlike Java or Python, where you need to bundle with your code also the execution machine, the virtual machine, or the interpreter. In Rust, you don't have to do it. So your final bundle, the extension bundle that you upload, in the end, the extensions are bundled as layers in Lambda, are smaller and takes less time to load. So again, Rust has the benefits here. So how can we create the extension? So we understand that we need an extension. We found out that extension will improve the performance in our example. And we chose Rust because, again, Rust compiles to native. It's fast, as it doesn't eat the resources that our handler needs. In order to compile, build, and link your extension, we're using Cargo Lambda. It's the same tool that we've mentioned in the second strategy. This tool, not only that it compiles and builds your extension, it's also the same tool. You're using the same tool in order to deploy your extension as a layer. Same tool, two functions. So how do you do it? You're using the build subcommand of Cargo Lambda. Again, release it. You want to release it in a release mode because as a layer, you have a size limitation of 50 megabytes. Anything in debug mode, it will be hundreds of megabytes, and you won't be able to upload the extension. And in order to upload the extension as a layer, again, the Cargo Lambda has a deploy subcommand, and it does all the magic for you behind the scene. As simple as that. So if you remember, I told you that extension has its own lifecycle and its own API that it needs to interact with. It means that an extension also has its own runtime. Very similar to how we've developed our Rust Lambda, we need to do something very similar for our extension. We need to write a runtime, and we need to write a handler for extension. And again, we're doing it in the same code. No need to develop a runtime from scratch. We can use a crate that AWS provides for us, a code that is ready. So before diving into the code, I want to quickly do a high-level review on how the extension architecture might look like. So you have your handler. Everything in orange is the extension. Remember that your handler, at least in our case, the handler interacts with the extension using an HTTP server. It doesn't have to be. Specifically in this case, we are using HTTP server. It makes a post request against a local HTTP server. The HTTP server saves the analytics event into a channel. A channel is a mechanism in Rust that enables you to share information between two concurrent tasks. So you're writing the analytics data into a channel. And next, we have the extension handler that reads the data from the channel and sends it to our SQS queue. So let's look at the code. So again, we are starting with the runtime. Remember, we are writing both the runtime and the extension handler. So again, we're creating an async method. We are defining the channel, the mechanism to share data. And next, we are creating our HTTP server. And we are starting the event loop for the extension runtime. Again, it's a template. You can actually copy and paste it over and over again every time you're using an extension. Because your real code is going to be in the extension handler. And again, the extension handler is, whenever it's being invoked, it pulls all the relevant methods from the channel and sends these messages to the SQS queue. In our case, it's simple. Again, it depends really what your extension needs to do, but it's very simple code. And when uploading the extension, remember the extension is a layer, so you have to define the layer in your AWS SAM configuration. Great, so how do you use the extension? In our case, because we're using an HTTP server, you can use any HTTPS package in order to communicate with it. So here we can see an example in Node.js. We're using Access in order to do the communication. Performance. So unfortunately, the summary line, when the Lambda is invoked, you have a summary line in CloudFormation, in CloudWatch logs. And unfortunately, it doesn't contain the relevant data that we were looking for in order to get metrics about the performance. So we did some behavioral testing, and we used a curl in order to run our Lambda 50 times with the extension and 50 times without the extension and measure the performance. So let's look at the numbers. So when using warm start performance, you can see here that between 100 to 200 milliseconds difference between using the extension to not using the extension. So offloading the SDK sending to the SQS really proved itself. We really managed to lower the latency of the Lambda, the way at least that our customer experienced it. And unfortunately, not everything is sunshine and roses. Because of the way the extension mechanism works, we don't get really good cold start performance. Why? Because behind the scenes, when your extension starts, when your Lambda starts in a cold start starting, it will also load your extension for the first time into memory. So it takes time to load it and run it for the first time, and that's why we are getting not ideal cold start performance. Great. So let's do, again, a quick recap for the third strategy. We had a common behavior, sending to analytics that we wanted to share among multiple Lambdas. We didn't want to write everything from scratch in each runtime. Therefore, we've decided to use Rust. Why Rust? It's fast. That's why. Takeaways. So you're probably saying to yourself, listen, Effie, you gave a 5-star session. And I'm hoping that that's what you're saying. But are you really expecting us to learn Rust and rewrite our code in Rust? Do you really think we are crazy? Well, yes and no. You are not crazy, but I do expect you to use Rust in order to improve the performance and cost of your Lambda. And I want to share with you a short journey that I did in order to learn Rust without learning it for years. I highly recommend reading the official Rust book. Okay? Read the first 10 chapters. While reading the book, experiment and try writing Rust using Rustlinks. No more than 2 weeks of work. When you're ready, take a pet project, write a CLI with Rust, and you're ready. No, I'm just joking. You're not really ready. It takes years to master Rust. But you are ready to make an intelligent discussion with your new Rust buddies. Them. These are the best friends when writing Rust. I don't expect you to know Rust and to know how to develop serverless with Rust. It's difficult. I'll be honest with you. It's really difficult. And I'm really hats off for those who learned how to use Rust before these tools. It's really difficult, but these tools enabled me and our team to use Rust in order to improve existing code. Again, we didn't write an entire application from scratch. All we wanted to do is to replace certain parts in our code in order to improve the performance and cost. And this is enough for us. So when you want to start using Rust in your application, you can start, again, by using Rust bindings. Search for a piece of code that you think that is slow, and you can replace it with Rust. And if you can't find one, I can assure you that just by replacing your Boto3 code, as simple as that, you'll gain a performance boost. Next, when you feel more comfortable, you can search for Lambdas that you can replace from scratch. Start with small Lambdas. Use Cargo Lambda with AWS SAM in order to do that. And last but not least, you can use Lambda extensions in order to share common behaviors across a fleet of Lambdas. That's it. We are done. I know it's a bumpy and long road, but I really think it's worth it. I think that I really hope that the numbers I showed you will change your mind that learning how to use Rust is worth it. This is the code. The QR, one of the QRs is the code. One of the QRs, if you want to contact me, is my contact details. And that's it. Thank you, guys.